Hello! This beginner tutorial will show you how to blink LEDs with the wiringPi library and the Linux shell and using the C programming language. Here's what you need. You need a Raspberry Pi running the Raspberry Pi OS. Any version with a 40-pin GPIO header will do. You need a breadboard, a couple of LEDs, any colors, 2 resistors, 220 or 330 ohms, and a small jumper wire. You also need a way to connect the breadboard to the Pi. I will be using a T-coupler with a ribbon cable, but you can also use individual wires. The circuit build is very simple. I will walk you through the steps right now, but I assume that you know how a breadboard works. Start with the cobbler by inserting it fully into the breadboard. I have shortened the legs of one resistor and bent all resistor legs. The resistors are connected to GPIO ports 19 and 26 as labeled on the cobbler, following the BCM numbering scheme. Make sure that the resistor wires are not touching. All LEDs are connected observing polarity. Most LEDs have legs of different lengths, and in such case, the longer leg, which is the anode or positive connection, goes towards the resistor. The shorter LED legs are connected to the blue power rail on the breadboard, which in turn will be connected to any available ground pin of the cobbler. You can connect the breadboard to the Pi once you verify that the circuit is correct. Let's test the circuit first using shell commands. The GPIO read-all command will display all GPIO headers, including their numbers, descriptions, and current status. This table has 2 sides, matching the physical layout of the GPIO headers. There are multiple numbering schemes used with the Raspberry Pi GPIO, which can be confusing for beginners. I already mentioned the BCM numbering, which is printed on the cobbler connector. The GPIO command is part of the wiringPi ecosystem, which favors its own numbering. Activating a pin to light up an LED requires 2 shell commands. First, you need to change the port mode to output, and then you write a value of 1 to it. Turning the LED off comes down to reversing the prior 2 commands. You write a value of 0 first, and then change the port mode to input. Let's test the other LED too. Restoring the port to default input state is very important. Ports in output mode will get damaged when accidentally connected to ground or 3.3 volts. This is why a current limiting resistor is needed when using the ports with LEDs. While the resistors protect the LEDs from too much current, the main role of the resistors is to protect the GPIO ports, as the maximum current drawn per port is only 16 mA in the current generation of the Raspberry Pi. As much as it is within your control, you should always make an effort to correctly deactivate GPIO ports after you are done using them. Let's write the simple program in C, which will alternately blink the 2 LEDs. You can use any text editor. I suggest Nano for beginners. The wiringPi library is installed by default on the Pi, and I use the include directive to bring it into my program. I will follow the default wiringPi numbering scheme and define the port numbers for each of my LEDs. wiringPi is initialized by calling the setup subroutine. Each pin is controlled separately, and just like in the shell, I start by setting the pin modes to output. Blinking LEDs comes down to turning them on and off based on a delay, typically using a loop. The green LED comes on for half a second and then it is turned off. Then the red LED comes on for half a second and it is turned off. This process continues over and over as this loop is infinite. A C program needs to be compiled before it can be run. The standard Linux GCC compiler will do that. This command needs 3 parameters. The wall option enables additional compiler checks. While not strictly required, it is standard practice as it detects minor issues and ultimately helps you write better programs. The wiringPi option is required to link the wiringPi library to the Blink program. The C source file name goes at the end. This is all case sensitive. Make sure you type it as you see it. A successful compilation like that will produce an executable file called a.out. This is the actual program which will be run. It already has the correct permissions. Beginners often try to execute the source file, and it is important that you know the difference between the 2 files involved here. The .c file is the code which you make and edit, while the a.out file is the binary executable. The compiled program is executed using the / prefix followed by the a.out program name and the enter key. The normal exit path in a program under Linux is pressing the Ctrl+C key sequence. This sends a signal to the program telling it to end. This program will end when I do that, but as you can see, one of the LEDs remained on. Looking at the GPIO read-all output, both ports used remained in output mode. I will use shell commands to restore the ports to default, but this should be the Blink program's responsibility. Let's add the necessary code to the program to deactivate the pins used before the program ends. This in itself is not sufficient, as the program will actually never get there. The keyboard interrupt Ctrl+C signal ends the program immediately, somewhere in the middle of the infinite loop. Fortunately, the Ctrl+C signal can be trapped, and we have the ability to provide code to override the default abrupt program exit. First, I will change the loop so it is no longer infinite, to depend on a variable instead. The program will start with this variable set to 1 and the LEDs will blink as before, but I can write a simple subroutine which will change this variable to 0, terminating the loop. The signal library provides an easy-to-use interface to call such subroutine whenever a program receives a signal. In this case, the program is told to call the cleanup subroutine if the Ctrl+C signal is received. With the signal trapped, the program will not terminate immediately. Now the loop will end its current iteration when the signal is received and proceed to the port deactivation code. Only then will the program end. Other signals can be handled the same way. For example, I will provide for the situation when the program is terminated using a kill command and when the terminal window is closed with the program running. Don't forget to recompile the program after making changes, otherwise you would be running the old version. While I'm at it, I can also change the compile command to receive a specific program name output instead of the default a.out. The updated program works as before, but now the ports will be deactivated correctly when I press Ctrl+C. This can be confirmed by using the GPIO read-all command. Let me run the program in the background to demonstrate the handling of the kill signal. Processes can be killed using the numerical process ID or their name. The ps command is used to determine the numerical process ID, and you can use that number to terminate the Blink program. The ports will be deactivated correctly as the program provides for that. You can skip the numerical process ID lookup and kill a program using its name. Keep in mind that the pkill command will terminate all programs with the matching name, which may not be always desired. Notice that I use the compiled program name and not the .c source file name, and I do not use the / prefix with the pkill command. Right now, the program uses the default wiringPi numbering. But wiringPi supports other numbering schemes as well. I actually prefer using the BCM numbers as that's what's printed on the cobbler. The BCM numbers for the ports used here are 19 and 26, and this can be easily changed in this program. Other than redefining the port numbers, you need to call the wiringPi setup GPIO subroutine instead of wiringPi setup to let wiringPi know that this program follows the BCM numbering. The rest of the program remains unchanged. Don't forget to recompile before running it. That's it for the basics. Keep an eye out for a follow-up video which will show you how to use buttons. Thanks for watching.